Okay, we can start. Sorry about that. I want to go over a couple of little common mistakes with the homework.
Yeah.
There's one thing I didn't take off on because I realized I didn't really give you a lot of good instructions on them. And also there's no really good rules for them. So one thing I didn't want to, and then I want to go over something with determinants because people are doing kind of painful things with determinants that are making life hard for yourself. So let me start with determinants.
Did you cry many times during this course?
No, not much. Okay. So a very useful way to solve determinants is the following. So let's say I have something like this: A, B, C, D, E, F, G, H, I, something like that, which is what we have in the eigenvalue eigenfunction problem. Now, what's the standard? What do they teach in math? Which is not wrong.
You take the first element of the first
You
row
start with A. What do? You cross out. You take A.
and multiply by the determinant stuff that's there.
Yeah. So you cross out this column. And you cross out this row, and you look at the little 2 by 2 here. So you say this is E, F, H, I. Then you hop over to B, and what happens with the B?
They fly. Make
Okay,
honey.
they make honey, they fly, okay. The sign changes, because remember that the cofactor term there, you get this minus B. And then what do? You cross out this column and this row, and then you look at the determinant formed by the other column. So this is D, G, F, I. And then what do? You hop over to C, and you do the same thing. You're going to say C. So you cross out this column and this row, and you look at the little 2 by 2 formed here. And that's perfectly fine, and that will always work. However, I think usually whenever, just what I've noticed by experience, I can't tell you why this works, but it's always been my experience. This way here often doesn't show kind of the easy way to solve these things. I would argue actually the easiest way to solve this is, let me make this bigger. I think that's gonna make a bigger version of this so you can see it easier. Right. Okay, and you've seen me do this before. Yes, you grunt. Okay. So you multiply all these. That comes under a plus sign. Where's my next grunting go? Just more fun when you grunt like you're Tarzan. Okay? This. And that comes under a plus sign. And then you add to that. This way. So what would this be in here? This would be then A, E, I. Okay. Plus D, F, G. Then plus C, H, D.
That's us. You have to, for like next time you show this, you have to pick up the letters that they spell something.
See, people try that in classical mechanics when people take it. I show them how to do these really kind of amazing things by manipulating indices. They always try to make them spell things. They go for the joke and mess up the. No, you have to be careful of that. So we have that. Then what do? We do the same thing in the other direction, but they come in gotcha. This guy. That comes under the minus sign. This guy, and then this guy here. And they all come in with minus signs. Then minus G, E, C. Minus H, F, A, minus I, B, D. Okay. I think if you do it that way, and then look at what you can factoring out the common terms. Okay, then factor out common terms. Because a lot of people, when they solve this problem, they ended up with this weird cubic, and then magic happened, and there are roots. This is actually if you do it this way here, just factor the common factors. It's really, really easy to do. Again, it comes out quite nice. Okay. So again, it's not that you can't do it. Some people solved it with computer system, which is fine. They did the correct thing. If you'd have solved this with Wolfram Alpha or mathematical or Maple, what would you always do?
Get complex roots or?
Write it down then.
State what you did, and people did that. That's the correct thing to do. So if you have something like some big expression, and then all of a sudden there's an answer, no. But if you say, oh, I use mathematical from alpha or Maple, that's perfectly fine. But then you state that you did that. Then I'm usually going to make some like you don't have to do this and stuff like that. But it's not wrong to do. But always state what mathematical system you use. Otherwise, somebody's going to say, how? Okay. But if you state it, then that's perfectly fine. Okay. Now the ones I'm going to give you are going to be things that you can do by hand. Okay, that makes sense? Okay. So do this. I think this method is almost always easier, and then always factor out the common terms. So for example, and this one here.
Can you just go over what was in the homework problem?
Yeah. So you ended up with a determinant. Does anyone have it here? Yeah, so you have this guy here.
Oh.
So you have this guy here. And why did you find lambdas? So what do? Okay, let's just set it since you have a test coming up.
Set up a negative value.
Okay, so this would be A.
Vector.
H is acting on some eigenvector V. If this is truly an eigenvector of H, what does it give us?
A constant times the
This lambda V. Then what's our standard trick? We multiply by 1 in a clever fashion, which is
identity matrix.
put the identity in here. Then we take it to the other side and factor out the V. Now, what can't this thing have?
That's 0.
That can't have an inverse, because if it has an inverse,
Then you get a trivial solution.
you get the trivial solution. So how do we guarantee that that has no inverse?
Determinant.
The determinant has to be 0. Okay, that guarantees that that has no inverse. And that gives us the non-trivial solution. So you're going to have, when you do this, this will give you 5 minus lambda 5. Doesn't give you that at all. 5 minus lambda 2, 0. 2, 5 minus lambda 0. 0, 0, 6 minus lambda. And if you do it my way, what does that give you? That's correct.
5
What's
minus.
the first?
Across the day.
Okay, so this is 5 minus lambda squared. 6 minus lambda. What happens if it goes? You get zeros. Now what?
Now you grunt with the minus sign.
We grunt the other way. Giving. Minus 4, 6 minus lambda. Now what would you do? Always factor out your common terms. So what one of the eigenvalues have to be? 6. 6, right? So this equals 0. So this is lambda equals 6. Okay. Give me the smart way to do that one. Do not use a quadratic. It's not wrong to use a quadratic, but think.
Difference of squares.
Yeah,
What? Why not? What's the problem with that?
just do the dumb
I
thing.
mean, it's,
Okay, well, this has to equal 0.
yeah, so it's either a 3.
So this guy here, what do you do? Square root both sides. This is, don't do the plus or minus on both sides, you only do it on one. And then just solve for it. This is 5 plus or minus 2 equals what?
Either 3 or minus.
So your lambda is 7, 3.
It did difference of squares. It pops up in one action.
I think that's all you do.
No, it's personal.
Yeah. Acquired taste. It's like Brussels sprouts, an acquired taste. You either think Brussels sprouts are the greatest thing ever, especially with bacon. Because that's what you do if you had bacon anything. Brilliant, okay? Does that make sense?
Yeah.
Questions? The other thing I want to say a little bit about drawing the disconnectivity graph. I mean, for the most part, all the homework's well, all the mistakes are kind of on the order of like, why do you do that? Just kind of stupid things. So yeah, this guy there. So with the disconnectivity graph, we had something like this. Put it lower. Oh. One, two, three, 4, 5. A, B, C, D. Okay. The question is, what does this connectivity graph here look like? So look at the like little pieces first. Okay, so let's draw this little piece here. So what would that look like?
A splitting into 1 and 2.
Yeah, so this would be, here's your 1, here's your 2. You'd have something like that. Okay. Now, how do then, now let's go over and look at this mess over here. There's different ways of doing this. Okay, so I have my 3, I have my 4, I have my 5.
So between 3 and 4, there's a C, and between 4 and 5, there's a D.
Yeah, so don't do the following. And again, the reason why, it's not that it's just never seen them like this. This is C and D. Basically, you got these things that look like M's. Now that was probably the most common thing. I didn't take off any of it on that because I didn't really tell you people what to do with these things. It's clear what that means, but it just looks ugly. Okay, so this has the problem called ugly. Okay, and no one draws them. Okay, so how would you draw them? There's different things you could do. So when you do these things, you never have this. You always have things that are more like this. You never have things like that. They always kind of go up. So what would you do here? Instead of having this guy here, actually. Yes, try that with PowerPoint. Okay, you can't do that with PowerPoint.
No, boards make that sound.
Yes, they do. It's a skill. Okay, so can't do anything else, but it's a skill. So you could do the following. You could say, well, I could maybe go like this, here, like this, like that. I could go like that. That would work.
Connected.
What I could do is, and they're still connected here. Okay. What I could also do and say, well, and sometimes people do this. These more or less look like the same energy.
Yeah.
And so what some people did, and that was fine because I've seen this in diagrams. I've seen something like this. Where they kind of have like a C, D here like this. Then they have the 3, and the 4, and the 5. I've seen this in diagrams like this. And so the main thing is don't have mountains. Okay. Now what do you want to do? You want to connect these guys together. So like over here. Here's my B, and kind of go like this, and then like that. You had this over here, and it'd be like that here. Something like that. They look kind of aesthetically appealing when you do these things. And again, when you do these things on the simple cases we had here, there's not a lot going on. But when you get more involved things, it's you really have to sometimes rely on these kind of things. Okay. Again, if you had, I didn't take off of that because I didn't really set it up well enough. Good. Okay. I want to say a little bit more about estimating the vibrational time scale. And then we actually start looking at classes. Wow. You could say, I hope so, it's April and finals coming in May. So. Initially, some of the stuff we do is probably going to bore the glass people, but there's a lot of people in here who are in physics who don't have the glass background, so I have to set up some things for you. So glass people might be a little bit bored for a little bit, but I have to set things up. I want to have to show you how to count atoms, because it's not that it's hard, but there's kind of a weird, when your atoms are shared, you do little odd things, and it's not hard, but you've never seen it before. You have to have somebody explain what to do. Okay. Well, that said, we had a problem last time. The last time, we were estimating the vibrational time scale for the Morse potential. So that's our Morse potential. What was our Morse potential?
So with an exponential in it.
We had C naught to begin with.
1 plus.
Okay, we got a 1 minus e to the minus alpha r minus r naught.
Close the parenthesis.
Close the parenthesis, then that comes in squared minus 1. That's what we have there. And if we graph this thing, it looks like this. We got this guy like that. This guy was. This is our R naught. R naught many things, but here it's actually the minimum.
Okay.
Okay, so sorry. And then this fellow here was then ended up being our minus D naught. Okay. And we did a couple of things. We took the first derivative, we took the second derivative. What was our second derivative again with this? We evaluated it here. There's like 2 alpha squared D naught. We had that. Now, what did we do with this? We said that if we're in the vicinity right here, this looks like a simple harmonic oscillator. Come over here. Here's our simple harmonic oscillator. And so what I said is that we could say that this V is R plus this delta R equals this V at go ahead. I think we had an R naught. R naught. Then we had this 1/2, this guy here like this. We got that. Okay. This guy was our. This was our minus D naught, and this is a constant. Okay. And then what to do? This guy then turns out to be our buddy here. This is our 2 alpha squared D naught. But if you look at this whole thing here, what did we say that whole thing is?
The potential. The harmonic oscillator.
Yeah, we compared it to the harmonic oscillator, which is what? 1/2 kx squared. And what is the x in the harmonic oscillator?
The change in displacement.
Yes, the change is basically how much the spring has been compressed or elongated. It's basically the distance from here. In other words, if I'm over here, this is R. This distance right here, this is my delta. We're looking at these vicinities right in here. And we also then worked out if you remember, we know that our natural frequency of oscillation was the square root of k over m. And so in this case here, what did this become? This value here is our k, m over 2. Yeah, so we took this guy and put it in here. This is the square root of 2 alpha squared d naught over m. And what did we find out about this omega? 2 pi over the period t. And so this period t here is going to be this 2 pi square root of m over 2 pi alpha squared d naught. We said, what is this period here? That period is the
approximately the time scale.
It's going to scale the vibrational time scale. So we said that this is going to be a good estimation for a vibrational time scale, and that is showing up even. Does that make sense? Now, life was good with the exception of one little thing. What did we say happens to our little buddy M?
Well, it's not one mass oscillating, right? It's a,
Yeah, we actually have two masses going together, and so this is kind of a fine point, but I want to go over it. I was gonna give you another daily homework on it, but I figured with everything else going on, I thought, I don't really want the tire slash on my car. So I thought maybe I better not have like another daily homework until after the second class. Okay, so there is one correction you need to account for. You need to account for. I want to set this up. A lot of you have already seen it, but some of you have not. Is that M must be replaced. And I'm going to tell you why this is the case. By the reduced mass mu. Where this mu is going to be M1, M2 over M1 plus M2. Because what we really have, we have M1 here, some sort of, I'll put a spring between the two, here's M2, that, and that, this M here has to be replaced by mu. So what we really have is that this vibrational time scale is going to be this 2 pi square root of mu over 2 alpha squared g log. I want to show you why you need that. Okay, who would know this? This would be fair game for Sarah, Denise, Etchell, Lauren, Josh, I think Ryan. I think that's it.
are you skipping other people?
Actually, no, and Matt, no, Matt was a no. Okay, Garrett, Eric. Garrett. So a lot of people here. Fair game, fair game. Okay. Dominic. Okay, so let's say here's our first particle, M1. This is M1. This is R2. And this is M2. And this distance right here is a separation distance R here, which we call
R2 minus R1.
R2 minus R1. Now, where would be the center of mass of this problem?
R1.
It'd be someplace in between here. Who knows where it is? This would be the center mass here, R. And how do we define the center mass? Well, if there was like a massless wire connecting these two, I could put my finger there and balance the system.
Yeah.
That's what it means. How do we formally define the center mass?
M1.
Yeah, as a
It's a weighted sum.
Yeah.
It's M1 R1 plus M2 R2 over the sum of the masses. Okay. Now, if I write the energy for this system, how do I write the energy for the system? Okay, what's energy always given by?
potential plus kinetic.
So kinetic plus potential. Okay, this T is not the period, it's not the temperature, now it's kinetic energy.
Yeah.
Okay, so we're using T in three different ways. Sorry about that. Okay. This is not the volume, it's a two-body potential, not the velocity. Okay, so how do we write the kinetic energy always?
And FOD squared.
So what would it be in this case?
It would be the sum of kinetic energies of both.
Yeah, that's the E here is going to be the 1/2 M1 V1 squared plus
2 V2.
1/2 M2 V2 squared plus the potential energy. And we're taking a two-body potential energy.
So
So this is going to be a two-body potential.
V of R1 and R2.
And we're going to make the special case here that we're going to take a very special type of potential energy, call it A. Let's see if you remember. What would that be only depend upon?
Separation
The
distance.
separation distance. And when you have something that only depends on the separation distance, you call that a central
Central force.
potential, when it gives rise to the central force. So we assume that two-body V is a central force. Is a central potential. Which means V only depends on the separation distance. Only depends on the magnitude of R. It means something else. It means that the force is always directed
Along that vector.
yeah, along the line here. So along the line connecting these two, that could be an attractive or repulsive force. When you have all that, you call it a central force. Now, something really amazing happens when you have a two-body central force problem. Again, for those of you who had classical mechanics, you know, we have that whole section on this.
We
Is
did
that an
that.
R1 or a V?
Oh, that's an R1, but you can't tell that what it wrote. It looks just like a V.
We have that in modern as well.
It gets repeated for the bit.
And in Geo.
It gets repeated for the bit. I believe that the only way things stick in is you have to see things again and again. Then after a while, you'll.
It's 100% true.
That makes perfect sense. Okay, so what we're going to do is we're going to rewrite that expression in terms of the velocity of the relative coordinate and the velocity of the center mass. So what we're going to do is rewrite this expression. In terms of the coordinates R and R. Okay. Let's do that. So, okay, this is kind of a stupid question, but I'm going to ask it anyways. Do you want me to leave this as a daily homework that you can crank out and show me the result, or do you want me to do it on the board? Board. As I said, I think I prefaced this by saying I think this is a stupid question. Okay, don't you do that. Okay, so let's go through and do a couple things here. So what is going to be V1?
The ER1.
The dr1 vector dt. What is in V2?
ER2.
The RD2 dt. Which was I2D2's brother. Okay. Never made it into movies, so bad actor. Which you'd think that being Star Wars, they would have been hired on. Well, it turns out they didn't, so. Sorry, okay. So now what do? We have this fellow here, we have R, so we need to write R1 and R2 in terms of R and R. So let's do that. So we have R equals R2 minus R1. And our big R is M1 R1 plus M2 R2 over. Okay, let's solve these crazy things. I'm going to take this over here. I'll solve this for, let's say for R2. So R2 is R plus R1. And I take this and put it in here. So I can take over the mass term. Here's my M1 R1. My R2 is my buddy here. I can group my R1s together. And take this over here. I'm gonna take this over here. And I'm gonna divide through by the mass from here. And if I do that, I'm left with this. Cool. Does that make sense?
So for R2.
Can't wait to find out. Then if I want to solve for R2, I do the same thing. I think it comes in with a plus sign. But likewise,
You can just please use the first equation.
well,
Please use the first equation.
yeah, that's what I was gonna do. I was just actually gonna do, that's just gonna write it down. If you take this and put it in here, do you mind if I just write down the answer? Okay, this may not work. If it doesn't, should have put it in the steps. Okay, my memory tells me it's this. Let me do a little thing here. I think I believe it. Okay. Now, how do we substitute that in here? We need the velocities here. So what is V1 again?
DR1.
Yeah, I take the derivative. So my V1 factor, which is
That's right.
sitting out there. So my V1, which is dr1 dt, equals my buddy over here. That's wrong. That's a 2. Yeah, that's good. So I'm gonna take the I have to take the derivative of all this. So I get a dot here. I get a dot here. What does a dot mean again? Dot means a time derivative. So what I have to do is I take the time derivative of this guy here, so I just get dots with these guys. And likewise, I have the following. We end up V2 is dr2 dt. That'll be r dot plus m1, m1 plus m2 per dot. Have here, I wrote the energy. There's only one subtle spot. What does V1 squared mean?
V1 dot V1.
Okay, it's V1 dot V1, so it's V1 vector dot V1 vector, right? This fellow here is really V1 vector, not V1 vector. This from here is V2 vector, not V2 vector.
After that,
What?
is the term in for potential function R2 minus R1?
Yes, yep,
Got
okay. So if you do this, what happens here? You get E equals 1/2 M1. Well, if I dot this into itself, what do I get? I get R dot R dot. Okay. Plus M2 over M1, M2 with a 2. Actually, there's a minus up there. Dot dot R. Here,
Sure.
and then plus my M2 over M1 plus M2 squared. R dot R dot.
You forgot a time derivative on the second term.
Thank you, yep. Everyone happy with that? That's this guy here. I do the same thing for this one here. Okay, I'm doing this because I know when I was an undergraduate, and at some point, the mass became mu. I had no idea why. And it drove me nuts that no one showed me where it came from. Just, I did not like the whole problem. Usually, if I didn't know where something came from, I stopped. I went, no, I don't get it. Okay, so if you're screwing my buddy here. That's why kinetic energy. You can see it made life a lot easier. And so I'm glad we made this change. And then this guy just becomes this in the sphere at the magnitude of R.
Those little words don't need to have a dot above the red.
Oh, thank you. Oh. Keep me honest. Now something great happens here. A lot of great things happen. So first of all, what is this R dot here? That's going to be my velocity of
The center of mass.
velocity of the center mass. What about my little R dot?
That's the relative velocity.
That's going to be the relative velocity. I'll call this little v like this. Now something great happens in this expression. What happens to these cross terms? They cancel. You can see this term here is multiplied by M1. This term here is multiplied by M2. So those cross terms cancel. Okay, so what happens if I have the velocity of the center mass out into the velocity of center mass? Okay, the velocity of center mass squared. So I'm left with E equals 1/2 M1 V center mass squared plus 1/2 M2 M1 plus M2 squared V squared from my buddy here, M1. I got this guy here.
That's loss.
Yep, yep, that means that I'm gonna ink it over. Plus 1/2 M2 V center mass squared plus 1/2 M2 M1 over M1 plus M2 squared V squared big V bar like this. Okay, hell's almost over, I promise.
Still the purgatory, that's the last.
This is symbols that you have, like, it's like the R dot,
Which guy?
it's like this like weird B or new or.
Oh, this is just a velocity, it's like a script V. Just to distinguish it from all the other groups. So I can group all the center mass terms. Then I can group all the other terms. Okay. How do we interpret this guy here?
It's the mass of the total mass of the system.
This is total mass of the system.
So it's the kinetic energy of the center of mass.
Yeah, so in other words, let's say I have, what's a good example of central force? which you always use in physics. Gravitation. So let's say here are two stars orbiting each other like this. Here are two stars. Well, chances are, what are these two stars also doing in space?
Spinning.
They're also most likely going through space like this. So what does this term then represent? There's a mass in some center. There's a total mass for that system that's going this way. So that system here, there's a kinetic energy connected with that center of mass. And that's what this term is here. Okay, now this term looks awful. So what do? Let's make it look pretty. Let's factor out an M1, M2 out of the whole thing here. Factor out an M1, M2 here. And that leaves me, I can pull up the masses in the bottom too. I do that, I'm left with M2 plus M1 B squared. One of those go out and Shazam, we are done. Okay, so this gives me 1/2 M1 plus M2 B center mass squared. It's 1/2 M1 M2 M1 plus M2. Okay. What does this look like?
Forgetting the potential energy.
What does that look like?
It's a definition of mu.
That's the definition of mu. It looks like it has the units of just one mass. But this to be formally defined to be. Yeah. That's your reduced mass. So what have we done with this problem here? We've taken this problem this way. Okay, so let's say here's our two here. Here's our center of mass. Now, what do we know about the kinetic energy of the center of mass from here?
That's completely separate from the kinetic energy of the.
This is actually a constant. One way you can see that is this way here. It is a constant.
Plus the center of mass accelerating.
Because there's no external forces in there.
Oh, yeah, you're right.
It's not possible. So this term right here is a constant. One way you can actually see how we can get rid of it is I can always take my coordinates to be anywhere. So it would be a good place to take the coordinates.
Center of mass.
At the center of mass here at 0. Okay. Then what's going to happen here? Well, since there are no external forces, the center mass doesn't change. That's going to be 0. So this is basically a constant term that I can kill. So I've taken two masses here. And what have I done with it? I reduced it to one object of one mass. The separation R. I've reduced this problem here. This R, here's my mu like this. I've taken the two-body problem and I've reduced it to a one mass problem. Okay. Tremendous simplification. But this only works for
No external body forces. So like central potential.
you have to have a central potential, central forces on here. And how many masses?
2.
Only 2. Okay, so if you try to do this way, like 3 bodies, it doesn't work. Okay, the 3-body problem is actually a famous problem you do in physics, and you can't make a lot of practice. You can't go very far. You have to make a lot of simplifications. But it's one of those people always the really high-end physicists always try tackling the 3-body problem. In quantum mechanics, you can solve it exactly, and if you understand what exactly means in the proper sense. Okay. Because my advisor would always say you can solve it exactly. And what do you mean by that? What do you mean by this?
Who's hand with that? Yours?
Yeah, because but he explains, meaning you can get the arbitrary accuracy. Any accuracy you want it, you can solve the problem for that accuracy. But my advisor would always call that exactly. Okay, that makes sense? So now let's actually destroy the time. Okay, the clock needs to go. Okay, okay, so all I want to do is put in numbers to show you how the units work. You can take another day and you can have that homework in later, because it's basically you just have to be careful with the units on some things.
Yeah.
Okay. None of it's hard, but I want to show you how to do it. And then during that thing on glass structure tomorrow, what I want to do is I want to talk about the Zachariason rules tomorrow. No one's going to be shocked by this, okay? The people who have not studied glass will be, well, it's not shocked. And then I want to show you how you count atoms in the system. And I want to start with, I just want to calculate what are called these Q ratios and alkali silicate classes. There's a cute little calculation, which is, it's not that bad. But I think it's a really good exercise in counting atoms. So I want to do the exercise in counting atoms. And once we know how to count atoms, then I want to go to constraint theory. Okay. And well, I want to put boron there too. You have to have real. Have a great day. So tomorrow we get real glass system.